Welcome back, ladies and gentlemen. Hopefully you guys have had some success working through all the different ionic bonding examples, right? We ended up dealing with binary ionic compounds, polyatomic ionic compounds, multivalent ionic compounds, or transition ionic compounds. Now we're moving away from ionic compounds. This is usually the step where two things happen. One, everyone goes, oh, this is so much easier. And then two, they immediately get confused with the previous step. So be careful, but you should be fine. I mean, you have done this before, right? So this is going to be on page 20 of your notebook, and it is covalent compounds, right? Covalent compounds are ones made with non-metals. So if we take our periodic table here, right, metals are everything on this side of the periodic table, right? That's the staircase that divides them. Non-metals are the much smaller section up here. Now, we are primarily made of non-metals, whereas most of the rest of the universe is primarily made of metals. That is an interesting feature which results in all sorts of things that we'll talk about in more detail when we get further in the course. Right now, though, we're going to take a look at what it says here. And it says that nonmetals tend to combine chemically by sharing electron pairs. The key thing with ionic bonds, of course, is that, as we've discussed, you're transferring electrons from one to the other. They're moving. Covalent bonds do not move them, they share them, which means both of them keep a grip on it. We end up calling covalent compounds molecular, mostly just so we have another way to describe them. Now, the key thing about covalent compounds is that, and the key way with it they're different from ionic compounds, is that ionic compounds follow patterns, right? The binary ionic compounds followed a pattern that was on the chart, right? So we were able to do stuff like go, okay, so this one is one step away from the end. That means it must be -1. This is 2 steps, it's -2. 3 steps, -3. 4 steps, -4, or +4, because I could also start going backwards. All of that is a pattern that we could follow. So that was great. Then we saw the transition metals, the multivalents, which of course come up on this page. This page here shows all the multivalents and the various flavors that are possible. I mean, I should rephrase that. It shows some of the possible flavors because there's lots of different multivalents. Then we have this page, which shows the polyatomics down here. So we have so many different pages all showing ionic bonds and all the different ways that they can behave. But here's the thing. When you're sharing things, there's more than one option. Ionic bonds are about take and give. There's only so many ways that I can give you something. Like, I have it, I give it to you, you have it, we're done. But sharing, I could share 1, I could share 2, I could share 3, 4, 5, 6. There are so many different ways to share compared to give and take that we have to be careful. For ionics, when we're doing the names of things, we don't talk about how many atoms there are because it's generally considered obvious by anyone who knows chemistry. But for covalents, things are a little different. When we're dealing with covalents, you have to be able to tell someone exactly what we're dealing with. They have to know, because you can't just tell somebody, oh yeah, we're going to share between, let's choose 2 random nonmetals. We're going to share between phosphorus and sulfur. And you go, okay, how much? And they look at you like, well, don't you know? And you're like, no, because these guys have a lot of electrons. They could share a lot of different ways. Maybe the silicon only shares 1, or maybe it shares 5. You don't know, not unless they tell you. So the important part about covalent compounds is talking about the sharing, explaining the sharing, and covering all of the bases around the sharing. So in order to do this, we use prefixes. Now, a prefix is something that goes in front of a word. A prefix would go at the beginning compared to a suffix that goes at the end. Now, the prefixes we use for covalent compounds are Greek, which pairs up nicely with the Roman numerals we use in ionic bonds. The prefixes are for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here are the words. The first one is mono. The second one is di. The third one is tri. Then we have tetra, penta, hexa, hepta, octa, nona, and deca. You are expected to memorize these prefixes. You're going to need to know them. You're also expected to know how to use them. Now, there's a few extra things here. If you take a look here, there are a couple rules on page 20. And it says, name the first element in full using a prefix only when there are two or more of that element. That is, do not use the mono prefix if that is going on the first element. So an example here would be NO. Okay? NO, there's clearly one N, there's clearly one O. They're both nonmetals, so we know it's covalent. Okay, so this is a covalent question. And you'd think, okay, well, nitrogen, and you'd wonder, like, do I put a mono in front? Because there's only one of them. And the answer is no. We don't do that. Because remember, when we were writing different chemical formulas, such as the NO here that I just did, chemists are lazy. We don't put ones here, even though they technically should. We just assume that the reader knows that that means there's one of them because we didn't put any other number. So in the same way, we're just assuming that the reader knows that there is only one nitrogen. Now, the next rule says, name the second element and end it in IDE. Use prefixes to indicate the number of that element, including mono. So the second element here is oxygen, and so we go with oxide, just like before. But now we put mono in front. Now, the question usually arises, whoa, you just told us we're not doing it because chemists are lazy, and yet here we're doing it. What gives? Convention, it's kind of the rules, it's the way people behave or the way chemists do these things. It's weird, I know. Broadly speaking, I believe the reason is because that way, when somebody sees the Greek prefix, they know it's a covalent compound, just in case they get confused. But honestly, I don't really know. It doesn't really seem like they should need it, but they put it. However, there is a third rule that's going to change this final answer. Write the name of the compound, writing the substance found more to the left of the periodic table first. Okay, so basically what I'm saying here is that nitrogen goes first because nitrogen is more left than oxygen. But there is one other little rule. Monooxide, too many O's. English doesn't like having two O's next to each other. Yes, this part is technically Greek, but we're deciding to adapt its rules for English. So the extra O here gets removed. This happens to basically every letter except I. These two keep all the letters. The rest of them, the O's and the A's, will drop the O and the A if it's next to another vowel. So it's nitrogen monoxide. I've got a space here. I shouldn't. It should just be right next to it. So we'll just erase that and fix it. So it should look like this. Nitrogen monoxide. That is an example of a covalent compound name. So, again, the leftmost element, nitrogen's not on the left, but it's more left than oxygen. The leftmost element is written first, and you write it as normal, just like you did for ionic compounds. You only put a prefix if the prefix is different than one. Like if this was two nitrogens, then I would have written dinitrogen. Then you write the second element. The second element has an IDE ending. The reason for that, it's sort of a conventional way to say that it's a compound of some form, meaning two or more elements together. Finally, you put the prefix. When you put in that prefix, double check. Is it ending in an O or an A, and is it next to another vowel? If it is, you erase one of them. If it isn't, and it's die or try, you just keep it as is. You just keep it the same. And that's it. Those are the rules. So let's work through some examples. There's some examples on page 21. At the bottom of page 20, you'll see a couple words that are written there. These are covalent compounds that we just kind of expect you'll be able to memorize the names of. Water, I hope you've heard of this one. That's one you need to know. And ammonia, which is NH3. Okay? So, let's take a look at a couple other examples. The next example we're going to do is CO2, which you guys have seen many times before, probably in biology class or at the very least grade 10 when you guys were learning about ecosystems. CO2, of course, is the thing that you breathe out, like all animals. It's also that thing that plants need to breathe in order to exist. So, just like before, C is first. So it is carbon. We do not make it IDE because it's the first word, and we do not put mono in front because it's the first word. Second word, oxygen. Okay, well, we know how to do that. That's going to be oxide. But there's two oxygens, so I don't write monoxide, I write dioxide. Carbon dioxide, which you know that name. That name is one that you have seen and said and heard many, many times, but now you know what it means. Di means two. Incidentally, for those who have been paying attention and think, that those prefixes are reminding me of something, they probably do. A triangle is a thing with three angles. A tetraangle would be a thing with four angles. We usually just use the word square. A pentagon is a five-sided shape. A hexagon is a six-sided shape. A heptagon is a 7. An octagon is an 8. A nonagon is a 9, and a decagon is a 10. For those who end up being nerds, or at least those who like various types of role-playing games, 20-sided dice, dodecahedron. Dodeca. Deca means 10. Do means, in this case, 2 tens. 20. 20-sided dice. I'm sure no one is shocked to discover that Mr. C is a bit of a nerd. Anyway, 21, continuing with the next example. We've got N2O4. Nitrogen. But now it's a 2. A 2 is not a 1. I hope you know that. Which means that now I get to use the prefix. So this becomes dinitrogen, oxygen, oxide, and it's going to be tetra, but tetra has an A ending, so I remove the A. So it's going to just be dinitrogen tetroxide. And there you go. That's how you do it. Or at least that's how you go from formulas to names. What about names to formulas? Those were always much more difficult. Well, take a look at page 22. Page 22, we have an example here. We have dinitrogen monoxide. Okay. Now, for the purposes of doing ionic bonding, anytime we went from names to formulas, it was always difficult. We always had to pull out the periodic table, we had to flip through it to all sorts of different places, check so many things. It's an awful lot of work. We don't have to do it here. Covalent bonding is actually the only area where this becomes incredibly easy. Dinitrogen monoxide. It's got nitrogen and it's got oxygen. Those are the two elements. Okay, we immediately write those down. Nitrogen, N, oxygen, O. How many nitrogen? It tells you. Di, 2. How many oxygen? Mon, 1. Done. We're finished. Covalent bonding is pretty straightforward. The only part that tends to make things tricky isn't the covalent bonding. It's when you have to put them all together. The moment I ask you to go through a list of different elements and tell me if they're covalent or ionic, everything messes up. So, over the next several pages, you've got from 23 all the way up to, let's see here, 28 or so, you have got practice. Lots of practice. You're going to want to work on those. Now, since this is a pretty short video and this is a pretty simple one, I am going to talk a little bit about page 28. The practices and everything before that, you're going to want to do it. But for 28, we're just going to quickly talk about this. Because it turns out that covalent compounds have a small, friendly gathering. There's a certain pattern that arises in the periodic table. Specifically, all of the non-metals that are located in an L that goes like this and like this on the periodic table. These are called diatomic molecules. Think about that word, diatomic. We literally just learned, or at least reminded ourselves, what di means. Diatomic means 2 atoms. So there is a series of elements in the periodic table that take 2 atoms and put them together to make a compound, a molecular compound. So these things are discussed on page 28. There are numerous ways to memorize them, and you are expected to memorize them. The point of these, as we will learn, and well, you learned about them in grade 10, and we just simply said, these guys do this thing, it's kind of weird. What you will learn in grade 11 is that there is a reason they do these things, having to do with a concept called electronegativity. Now remember, chemists are bad at naming things. They usually name them what they are and then change the language so they sound smarter. So electro is electrons or negative charge thing. So electronegativity. Well, that's just negative, but like with more letters. So this is the measure of electric negativeness. What does that mean? Very broadly, I mean, we're going to go into more detail in like a month or so, but very broadly, it means that elements that are close to a noble gas on the periodic table, they're very eager to fill their valence shell, are very good at mugging every other element that comes by and stealing their electrons. Basically, electronegativity is a measure of just how criminal the elements are. The more electronegative, the more they're going to beat someone up in a back alley and take their electrons. So, these particular compounds will generally steal electrons if they can. But what happens if they don't have anyone else to rob? What happens if they're stuck in that back alley and there's nobody but them? Well, they're so desperate for electrons, they'll actually share. I know, the analogy breaks down at this point. Diatomics share electrons when there are 2 elements that are identical. Okay, that's the key. They have to be identical. So, for example, if I put hydrogen with hydrogen, they will share. And I will get good old H2. If I put hydrogen with, say, oxygen, they won't share, because the oxygen is a bit more aggressive than the hydrogen, so it will steal electrons from the hydrogen and call it a day. It'll also tend to find another hydrogen and steal their electrons, making good old water, but that's a side effect there. So what we're seeing is that diatomics only exist, this is key, they only exist if they are alone. If I take any other elements and put them nearby, they'll drop their twin and run off to go steal stuff from the other guy. That's key. So the elements that are diatomic are listed there. hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. I know the last one breaks the pattern. So here's the thing. All of them have very similar formulas. It's going to be H2, N2, O2, I want to make sure I put it in the same order as your notes, F2, Cl2, Br2, and I2 squished in at the bottom of the board, because I think at this point you can figure out the pattern. These ones are the diatomics. Now, when we are referring to these guys, we have sort of two ways we can do this. Because, obviously, I just told you that these guys will pair up, but I mean, maybe there's literally only one hydrogen in the entire area, right? We're like somewhere in space and there's no more hydrogen. Well, they can't pair up if there's only one of them. So we kind of have the situation where there are two different ways that we can find diatomic molecules, or sorry, diatomic elements. They could be paired up. They could be alone. As a result, when we are talking about them, there are two big things that happen, and one of them are useful and one of them is annoying. One of them is that we will call these atomic or elemental. So, for example, atomic hydrogen or elemental hydrogen, meaning it's as the periodic table of elements shows it. It is pure. We will call, in contrast, these ones over here a gas. So hydrogen gas or oxygen gas. The reason we will call them a gas is because, with the exception of the last two, all of these are gases. Bromine is a liquid. It's one of only two liquids on the periodic table. The other one is mercury, otherwise known as quicksilver, which is where the superhero gets his name. Iodine is solid. But the rest of these, all of those, are gases, so they just kind of lump them all together and call them gases. Almost all of the gases on the periodic table are diatomics or noble gases, which are all gases because they're noble gases. It's in the name. Now, the thing is, this may be atomic hydrogen, and this might be hydrogen gas, but, as previously mentioned, chemists are lazy, so they will sometimes refuse to use those extra definitions, and they will just say hydrogen and expect that you know which one they mean. I know, it's annoying. Generally, chemists will be talking about the gas form, these ones, the diatomics. The reason that's the one they generally talk about is because this is what you would find on Earth in some way. It's almost impossible to find these ones by themselves unless you do some fancy chemistry or you're in space where there isn't a lot of stuff. So because these are pretty rare and these ones are pretty common, most of the time when someone tells you, hey, could you pop down to the storeroom and grab me a cylinder of oxygen, they don't mean this one. They don't mean this one, they mean this one. And that's just part of the nature of it. Now, you need to remember this, and there are a couple ways. In your notes here on page 28, you see a couple mnemonics, they're called. They're sort of rhymes to help you remember things. There's Hofbrinkel in the cans of the clown. And there's also I have no bright or clever friends, which is a mnemonic that has the first letters of each word relating to which elements are diatomic. I don't actually use those methods to remember it. I just look at the periodic table and realize that all the ones that make the diatomics start here, go up, and then go over. It's an L. I mean, if you want to include hydrogen, which is way over here, then it makes a T, because you could put hydrogen there, for example. But hydrogen's easy to remember. It's pretty unique. So, Hofbrinkel, I have no bright and clever friends, or just the L in the top corner of the periodic table. Any of those will do it. Or you could just memorize every single one of these. It's whatever works for you. The key thing is you need to know them, and you need to remember, it is so important, I am stressing it again, that this only happens when these guys are alone. If I take these guys and I were to bring some, I don't know, an aluminum nearby, they would drop their sister twin so fast and run over to the aluminum in order to go make an ionic bond. Okay? So, if it's alone, diatomic. If it's not, it will be in some other form of compound. Okay. That takes you guys up to page 28. You guys should be able to do all the practice up to page 28 at this point. Hopefully you shouldn't have any problems. I will talk to you guys next time with some balancing chemical equations. Should ring some bells, and hopefully it won't be too hard. Cheers.